Mr. Bust, your poster is displayed on the screen.
Okay, ma'am.
Please explain.
Okay. Good afternoon, everyone. Myself, Ignesh Sharpat. My work on one-pot synthesis and photophysical study of biocompatible egg albumin cap nickel nanoparticle. The metal nanoparticle based work is the one of the growing field in the research community. The surface of metal nanoparticle is a key factor for affecting interaction with the targeted molecules. Reducing grain size to nanoscale increase the active surface area. Especially ferro nanomaterials is the very interested research field because these nanoparticles having application in various areas including bioimaging, biosensors, catalysis, and electronic devices. I have selected egg albumin as a capping agent because it having high level of amino acids and the proteins, which effectively controls the growth of the nanoparticle size. I have synthesized the nanoparticle by using simple chemical co-precipitate method. In this experiment, I have selected double distilled water as a dissolvent and nanoparticles, nickel nanoparticles were prepared by reducing the nickel chloride salts. The reagent used in the synthesis process is hydrogen dihydrochloride and reducing agent is nickel borohydride. Initially, by adding the reagent and salts, I have stirred the solution for 20 minutes, then add the sodium hydroxide to it. Then slowly the color changing from greenish to bluish color. Then taking the egg albumin as a capping agent and heat it up to 80 degrees Celsius and dropwise add the initially prepared mixture. After 20 minutes stirring, I add sodium borohydride to it. Then black color slurries of sample with evaluation of hydrogen gas will occur. This process is instantaneous exothermic reaction. Then kept it for 10 hours as it is at room temperature. After 10 hours, by using external magnet, I remove that black color slurries and by using double distilled water, repeatedly wash it for several times to remove the unwanted impurities present in that sample. The material, the obtained that solution, the obtained that slurries will be dried using oven and collected it in a airtight vessel. In order to confirm the formation of nanoparticle, I use the material characterization. Those are X-ray diffraction studies and SEM EDS studies. From X-ray diffraction, it is confirmed that the structure and composition of synthesized nanoparticles is in nickel form. Here, four major peaks are obtained at the plane of 111, 200, 220, and 311. Both shows FCC nickel structure. And I have determined the interplanar spacing, FWHM, and size of the synthesized nanoparticles. And also the interesting fact that there is no additional peaks are observed. That means without any impurity phases, we got pure FCC nickel nanoparticles. In XRD analysis, I have confirmed that undoped nickel nanoparticle size is 11.23 nanometer for doped, that is uncapped nickel nanoparticles having size 11.23 nanometer. For egg albumin capped nanoparticle shows 5.84 nanometer size. By using SEM analysis, the morphology of the nanoparticles will be studied. Here, in order to get distinct particle, here the images shows that there is a spherical shaped nanoparticles is formed. But because of poor resolution, I didn't get that clear image of the spherical shape. By improving that resolution of image and using that clear SEM pattern, it is possible to calculate diameter of the synthesized nanoparticles. The EDS is one of the best tools to get elemental composition of the synthesized sample. In the synthesized sample, I have got nickel, carbon, oxygen, and aluminum elements in that synthesis. The atomic percentage of nickel is 51.09%, oxygen is 32.45%. Here, the presence of oxygen with high atomic percent due to the considerable existence in the capping agent albumin. Later, I will study the optical properties by using UV absorption and photoluminescence.
Particle size from XRD and SDM or both.
Yes, sir.
Uh, from which characterization you have determined the particle size?
XRD, sir. XRD characterization.
XRD. Madam, any more questions? Hello.
Okay, sir, it's all right.
Okay.
Okay, thank you.
So shall we start with the next presentation?
Yes, sir.
Okay.
Next poster.
Madam, am I audible? Madam,
Please introduce yourself.
hello
Dear
everyone.
participants, please. Yes, Satyajit Patil, you are audible. All participants are requested, please introduce yourself first and then start your presentation.
In
Now, Dr. Shikha ma'am is with us. We are heartily welcome to the session, ma'am.
Thank you, madam.
Satyajit, you can start.
Good afternoon.
Okay.
Good afternoon, madam.
Introduce first.
Okay.
Good afternoon.
Good afternoon, everyone. My name is Satyajit Sanjay Patil. Today I am going to present my poster entitled as Electrochemical Performance of Nickel Phosphate Hydrate Microplates on 3D Nickel Foam for Supercapacitors under the guidance of Professor P.S. Patil sir, Department of Physics, Shivaji University, Kolhapur. As you know that Electrical vehicles' popularity is increasing day by day due to their eco-friendly nature. Recent electrical vehicles demand high power and energy density to operate. The supercapacitor is a catchy choice among all energy devices due to its interesting characteristics. Based on charge storage mechanism, supercapacitors are divided into two groups, such as electrical double layer capacitors and pseudocapacitors. Again, pseudocapacitors are divided into three categories as intrinsic, intercalation, and extrinsic pseudocapacitors, as shown in figure with their electrochemical signatures. In this study, we have synthesized binder-free nickel phosphate hydrate using the single-step hydrothermal method on nickel foam, as shown in schematic. The XRD pattern confirms the nickel phosphate hydrate phase with monoclinic structure with the standard JCPDS card number 330951. The FTIR spectrum confirms the various phosphate vibrational bands from 520 to 1068 centimeter inverse. Along with that, water molecule vibrational band were detected at 1384 and 3391 centimeter inverse. The BET reveals that 13.01 meter square per gram specific surface area of the sample. The SPM micrographs of all the sample at various magnifications reveals uniformly distributed nickel phosphate hydrate microplates over nickel foam. After that, the electrochemical measurements were performed using three electrode system in 1 molar KOH electrolyte with potential window minus zero point 0.2 to 0.55 volt. The CV and GCD of the sample at various scan rate and current density are shown in respective figures. To study charge storage kinetics, power law is used. It shows that the diffusion controlled behavior dominantly present in the sample, which indicates Faradic charge storage mechanism. Now, in Nyquist plot, electrode do not exhibit semicircle, which indicates minimum charge transfer resistance, nearly 1.1 ohm. The electrode's cyclic stability was studied up to 5,000 cycles. It shows 79.24% stability at the 100 millivolts scan rate. In summary, the electrode shows the specific capacitance of 855.12 farad per gram at 10 milliamp per centimeter square current density with 66 watt hour per kg energy density and 1250 watt per kg power density. This comprehensive study suggests that nickel phosphate hydrate microplates is advantageous for improving energy storage. Now, I would like to acknowledge Golden Jubilee Research Fellowship and DST PERS Phase Second and UGC DSA Phase Second programs at Department of Physics, Shivaji University, Kolhapur. Thank you, one and all.
Okay. So you tell me,
Yes, sir.
what are your observations from CV plots?
Sir, in CV's plot, we generally study oxidation and reduction potential of the electrode. And we can see that the working potential window of our electrode is minus 0.2 to 0.55 volt in KOH electrolyte.